This paper by meta researchers is about this higher order attention mechanism, and it has kind of been talked about a lot on like Twitter and stuff. So I thought it would be interesting to cover. So one thing is they call these the simplex attention. Um, so from a mathematical point of view, they don't actually use simplices, or they use basically just higher order attention. So I think it would be better to call this trilinear attention rather than two simplicial attention. Also, this name sounds a lot cooler. So real quick, just want to mention that for here they basically use this these three-way connections, this three-way relationship, versus normal attention, which would use a two-way relationship. Though for a simplex, you have a few more properties rather than just a three-way relationship. So you have here, you basically have this face here, which is like if we call this vertex 1, vertex 2, vertex 3, it'd be v1, v2, and v3 as a face. But you also, in your simplex, you would contain the edges, so v1, v3, v2, v1, and v2, v3, as well as the so all lower order, or all lower orders, so as well as the vertices themselves. But you also have an orientation, and you basically relate things based off like these. You don't relate things in the way that you would normally relate things. It would be based off like faces and stuff. And there is a paper on this by it was Bodnar who released it, or I mean he's the one who they're the one who kind of does a lot of the topological neural network stuff. So if you're interested in actual like simplicial attention, there is a paper on it called Simplex or Simplicial attention. I think that's the name of the paper. Anyways, I do think this is a interesting paper. Just want to mention it's not using simplices. It's using a higher order term, not simplices. So anyways, not going to talk about this anymore. Let's talk about the actual paper. So this attention mechanism basically is taking normal attention, which we know as this two-way, basically a relationship between our queries and our keys, and you basically form this quadratic, or this squared attention matrix, where this is, say, of size t by s. They basically say, well, what if we extend it into another dimension to create higher order relationships? And you may be thinking that's going to be expensive to compute, and it is, and they do things to fix that. So let's just walk through this and see what they do. So yeah, I think this is they do a good job of describing a lot of different things. They even show exactly how they implemented it. So I think it's a good paper. It's just wanted to mention that part about simplices. So let's just start with attention, go increase the order by 1, see how to make it actually a little bit more efficient. So to start, let's just talk about normal 2D attention. So if we have our queries, they have two notations in here. They call the input of shape n by d, but n is used in two different places, or it's used all over the place, but it means two different things. So if you see n in an equation over here, it means this is the number of tokens. This is what you would normally think n is. But if you see n in, say, there's going to be some einsum notation, which I'll talk about in a second, it actually means the number of heads, if I'm not mistaken. So I'm just going to be calling the time dimensions t, s, and r. So t would be the time dimension. These would be our 3 time dimensions. For normal two-way attention, it would be this. R would be the third kind of axis of attention we're doing. And I'm going to be calling n the number of heads, because that's what they use in their einsum notation. So this would actually be a t by s matrix here. And this would be a sum over s instead. So with that out of the way, the normal attention mechanism here is done by using, so you create your attention matrix here by doing an inner product on the queries and the keys, so QK transpose, where this axis here is like of size T and this is of size S. And if you're not familiar with ein-sum notation, this is what it looks like. If you are, feel free to just skip. I just want to mention it in case there are people who are not familiar with it, because that is what they use to... It's a lot easier if you define things in terms of ein-sum notation whenever you're doing higher order stuff. So for ein-sum notation for the QK transpose, if we have Q of shape, this is our batch size, this is our time dimension, and this right here is basically our head dimension, and this is the number of heads, n, and h is the per head dimension. So the queries are basically the same thing, except you have a different number of tokens. You could have a different number of tokens. I'm also not worrying about GQA, group query attention. If you were doing group query attention, then here this n would be lower, and you would have to do something. You would have to do a few extra things. So I'm not worrying about GQA here. And if you want to do the inner product here, you can use this notation in PyTorch or NumPy. Choose your favorite library, and it allows you to easily do this inner product. Like, it's easy to do an inner product here, but it's harder, it's more annoying whenever you have higher order terms. So basically this is saying this is the shape of Q, this is the shape of K, and this is our output shape. And it defines a matrix multiplication on H, because H is shared between Q and K, and it's not in the output. It's not in the output here. So that must be what we're doing the inner product on H, which is our head dimension. And B is just left alone, and then N is the number of heads, and we basically are moving the number of heads into the second axis, and then we have our T by S matrix here. So this right here is batch by number of heads by our T by S QK matrix here. So this is just the notation we're going to be using, and what you do after you do the inner product on Q and K is you do your softmax on here, or you do softmax. So softmax is just normal softmax, and you do it along the rows. So if we have our attention matrix here, you're applying softmax along the rows here. So for every row you apply softmax, and that's important because we're actually going to be applying it in a slightly different way to add the third dimension. And then the final thing you do is this vector, or the value product. And again, I want to talk about the ein-sum notation. So using the A we had above, you apply softmax to A, and then you want to do an you want to do a product with the values. So if this is T by S, and this is S by D, or I guess here H, you would do an inner product on S to get your output. And to do that, you specify the shape of A, you specify the shape of V, and you specify the output shape you want. And notice here, instead, S is defined in both, but not defined in the output, so that's what we're going to be doing the inner product on. And it's basically just defining the shapes you want, and it handles the rest. There exists only one way to manipulate these shapes to get this output in the right way. So the ein-sum notation is not ambiguous in that way. So yeah, this is just ein-sum notation. Just basically define your shapes, you'll get your output. So enough of 2D attention. We all know and love two-way attention. We all know and love that. How do we add a third axis? So to do that, they use these trilinear forms, or this trilinear form, which is basically this three-way inner product. So instead of having an attention matrix, which looks like this, QK, where this is T and S, instead we're basically just going to extend the attention matrix, just like you would probably think you would. So for normal attention, you basically have Q, which defines which output you have. So for normal attention, basically this first row would correspond to the first output. This would correspond to the second output, and so on. It's the same thing down here, the same exact thing, except we're basically going to have two axes of keys. And if you have two axes of keys, that also means you have to have two axes of values. Basically, in normal attention, your queries define the rows, and your keys and values define the columns right here, where the keys and the values have the same dimension, have the same number of tokens, which would be s. Here, we're basically extending that by saying, what if we add a second pair of keys and values? So what this could be is, for self-attention, these would all basically be the same shapes, where you would have these would all be the same shapes. So it's basically just extending this to add higher order interaction terms. So instead of having these pairwise relationships, you can have these triplet relationships. And also, it allows you to basically, instead of having two modalities, so think of cross-attention. For cross-attention, if I want to have, say, Q be my image and KV be some text, maybe I'm conditioning on text, then if I have KV be my text and Q be my images, then I would be conditioning my image output on these KVs from text. So I'm basically conditioning the image on text. If I add a third modality, I can now add a third modality, and it has all these triplet relationships. Maybe I don't just want to condition my image on text, I want to condition it on audio for some reason. Here I can do that. But in normal attention, you would have to do something else. So yeah, it's the same. It's basically how you think you would go about doing it. So this just defines the inner product of Q and K. So instead of doing QK transpose, we're basically going to be doing this QK transpose K prime. And you may notice, wait, the shapes don't work. This doesn't make much sense. You basically are doing an inner product using this three-way inner product here. So you can see here, L is indexing the dimension here. So we're basically summing over this, we're basically doing an inner product on this three-way inner product here. So if we have a matrix here, and we pick some I, some j, and some k, so some query, some key, some query, some key from k, and some key from k prime, then you do this, then you do the inner product like this, where L is indexing the dimension. So this would be a vector, this would be a vector, and this would be a vector that you're all indexing and summing up. So normal three-way inner product, it's just normal three-way inner product. Here you apply softmax, and notice here softmax is applied over j and k. So if we go back to the diagram over here, j and k are indexing the keys and the values. So normally you would apply softmax over the rows here, and you would get your output right here. Instead, what you're doing is you're applying softmax over these two-dimensional slices right here, and then you get your output. So it's very similar, it's just an extension into another dimension, where you're applying softmax over slices instead of just rows, because now we have more than one axis that we apply softmax to. So it's this two-dimensional softmax, and you can think of it as just taking this slice here and flattening it into a single vector, and then applying softmax over that. It's the same idea. So that's how you apply softmax, and then this right here is basically so we have our attention matrix here, which is what I showed as that volumetric space. Here is we have to multiply by the values, and note that we have two values. So again, like we have our keys, which define what we're conditioning on, and if we have our keys and values which define what we're conditioning on, and since we have this set of keys for, we have k, and we added k prime, we also have to add a v prime to define how we're doing the output multiplication. So here, if we have, say, s, which is going to be of shape t by s by r, where t defines the number of queries we have, s defines the number of keys we have, and r defines the number of k primes we have, the third axis we're adding, then the output, or then these values here, are going to be of shape s by d, dv, and r by dv. What you do is you do a Hadamard product with those to get something of shape s by r by dv, and you do an inner product along the two conditioning dimensions. So it's like you would normally do, where you do an inner product on S, except you have a second dimension that you're doing an inner product on. So you do it on S and R. So it's basically like you would flatten this S and R dimension and then just do an inner product on there. It's just here now you have this extra dimension you have to work with. And that's basically how they do their attention. It's just, what if we extend this to another dimension? And if you do that, you basically have to do a three-way inner product instead, a two-dimensional softmax, and a two-dimensional inner product over here. And it's literally how, if you look at the shapes, it's how you would think you would do it. It's just extending it into another dimension. So if we look at the pseudocode for their two simplicial attention, or two simplicial attention, you do an einsum over, so this is A here. A is an einsum. So what we had before is we had these two, and we just had these two here, these two matrices. We add a third matrix here, and note that all it's doing is it's doing an einsum where the inner product dimension is H, because it's in the inputs and not the output. Then we do softmax, and it's over two axes, so it's over -1 or -2. If this is of shape whatever by T by S by R, where S indexes K and R indexes K prime, that's an H, K prime, and T indexes Q, then we're doing softmax over S and R, so over the slice. Then here is the einsum of our attention matrix here. These are our values, so this is what we would normally have. And then we add the second set of values here. And note, we have S and R here, we have S here, we have R here, so it's an it's this two-dimensional inner product that we're doing to get our output. So, what I explained above. So there is a problem, and the problem, so, I mean, this is all kind of, like, this should make sense. It's just extending this third dimension, and it's just adding a third dimension, extending the attention matrix to a third dimension, but there is a problem, and the problem is with this, this rope. So, yeah, there's a problem with rope. So, basically, they look at rope and they say, there's an issue here. If we have if we have an inner product on two vectors, which is what you see down here, you can, like, you have this invariance. Basically, if you have a vector, you can rotate it however you want, and if you have another vector, you can rotate it however you want. If you do an inner product on those, the inner product it doesn't matter. It doesn't matter how you rotate them. Specifically, it's invariant to orthogonal transformations. So, as they note here, R. R is just your rotation matrix here. However, the problem is, if we go down here, they mention that, so note that the trilinear form defined in equation 5, which is the three-way inner product, is not invariant to rotation and the application of the same rotation to Q, K, and K prime. So if you apply the same rotation to Q and K and do the inner product, the inner product is preserved. They say it no longer preserves the inner product. So if you apply the same rotation to Q, K, and K prime, and then you do the inner product, the inner product is not preserved. So there's an issue here. We can't, if it's not preserved, then the idea you have with rope cannot be applied here. So they say there are two things you can do. You can either say, I'm going to redefine rope, or you can say, I'm going to redefine what we're doing, this trilinear operation we're doing. Instead, they say, instead of doing an inner product, we're going to redefine the trilinear operation to make it rotational invariant. So if you think about it, one way to do that is to just take the determinant instead of taking the inner product. So imagine we have three vectors here. So they mention 1 and 2 dimensions, but imagine we have, say, 3 vectors here. You can rotate this however you want, and they say it's invariant to rotation. So, I mean, that makes sense. The determinant is invariant to rotations. Basically, for this three-dimensional determinant, this three-way determinant, if you think about it, it's basically computing a volume for 3 vectors, and you can rotate this however you want, and the volume stays exactly the same. And to do that, there is this formula, which basically says you can take two dot products or inner products, or you can do this, which is equivalent to just two inner products. So the idea is, instead of doing an inner product on our vectors, so instead of just taking the naive inner product, which is not rotationally invariant, we're instead going to take the determinant, which is rotationally invariant. Like, it is rotationally invariant. You can rotate this however you want, doesn't matter. You're still going to get the same determinant. And that's going to be the operation we use instead of this three-way inner product. So instead of what we had above, where the attention matrix, the every attention score, is defined by the inner product of q, k, and k prime, instead what we're going to do is define every attention score as the determinant of q, k, and k prime. And that's because the determinant is rotationally invariant. So they mention here, like literally all you're doing is you're just replacing the inner product operation with this determinant operation. And note that from above, we know that this determinant operation is the same as two inner products. One inner product here, and one inner product here. So that means you just have to change your, it's not that much more computationally expensive, but now you have this rotational invariance, which is what you want so that you can apply rope. If you didn't have this rotational invariance, then you wouldn't be able to apply rope, or at least you would have to find another way to do it. You couldn't apply rope natively. They mention here, since equation 8 has two dot product terms due to this rule up here, so equation 8, it would modify algorithm 1 to use two einsums instead of one in line 2. Just defined above, basically the attention operation. The final equation weights S are computed by applying a softmax function on the logits above, so just on this determinant, on the determinants instead of the inner products. And similar to equation 6, the output for token I is then a weighted sum of the value vectors. So all you're doing is you're replacing your attention scores with these determinants. And they basically, like, the first thing you may think is this a valid operation? They have a proof basically saying it is expressive. And this here is basically showing that. They have a full proof in the appendix saying it is, though this does seem like basically, given a small dimension, it can do a certain problem, so it is still expressive, though I feel like there needs to be a little more, but they do basically mention that it is expressive. So yeah, that's the idea right here. Basically, inner product not rotationally invariant because we have three vectors. We can make it rotationally invariant by taking the determinant instead, and we do that instead of the attention scores, or rather the attention scores are now the determinants. So now we can deal with the problem of the model not being like that computationally friendly. So we already know that normal attention is here. They have n, like I mentioned above. N is, in this case, the number of tokens in your sequence, while in the einsum, this is the number of heads. So yeah, attention is an n, it's a quadratic operation, quadratic in time and in memory. So normal attention is quadratic. If we do this, like if we just natively apply the two simplex attention that they describe above, you get a cubic operation, obviously, because you're adding this third dimension. So that's a problem because it's already hard enough to compute quadratic attention. So we have a problem. And what they do is they say, and what was kind of the first thing done after attention was defined is turn this into a sliding window. And this will turn it from complexity n cubed to O of n by W1 by W2. So it's no longer n cubed, instead it is smaller than that, depending on what your window size is. So that's what they say down here. You can reduce the complexity if you basically do sliding window attention. So yeah, This is they do sliding window attention. What window size do they use? They use this arbitrarily, where W1 is the dimension of K. It's the window for K, and W2 is the window for K prime. So they use a 512 by 32 window. I don't know why. It seems like they arbitrarily picked that. They say we choose a window size 512 by 32, balancing latency and quality. So yeah, it's fast and it preserves quality. Sure. I mean, basically they choose a window size such that it is the window, or the complexity is similar to that of normal dot product attention, normal quadratic attention. And they basically want to show that under this, adding this third axis, using the same amount of compute is beneficial. So if you have, under the same compute budget, if we instead do sliding window attention, using this third axis, as opposed to full attention with two axes, it's better. And that's basically what they're going to show. So another thing, so yeah, that's just what they do up here. They say we use sliding window attention instead. Here, they say, let's create a Triton kernel for this. So they basically do flash attention, but over two axes. So for normal flash attention, you kind of have your QK matrix, where this is like K and V, and you have this window size here, this kernel size here, and you basically iterate over, you have a loop over the rows, and you accumulate the values for the queries into some outputs, and you keep scores for softmax. I'm not going to go into flash attention that much, but if you know how flash attention works, you basically know that you have a loop that basically accumulates over your key and values, so over these rows. And basically what they do is they add a third loop, which does the third dimension, and they iterate over, they have a loop going over this dimension as well. So there's two loops now. And since you have windows, it's fine. It's still computationally not that, it's computationally close to normal quadratic attention because they have sliding window attention. While if you didn't do sliding window attention, you would have cubic complexity because you have now an inner loop, or a third or a second inner loop. So you usually have one loop going over the queries, which is different kernels. You can think of it as a loop, but it's basically these different different kernels you're launching. This one, and then each one basically has a loop going over your keys and values, but now you have a loop going over KV primes. So yeah, I mean, if you're curious, they have some code at the end, and the code is, you could probably code that up in Triton and it'll work quite well. They also have the backward pass, and they have code for the backward pass. But basically, it's very similar to sliding window attention. Not sliding window attention. It's very similar to flash attention with the sliding window. They also have this trick they do where they kind of merge K prime and Q before they do the inner product with the last key. So that's another thing that you'll see if you look at the Triton code, if you're interested in that. Like I said, if you know how flash attention works, it's very similar to that. It's basically just another loop that you add. So here's a sexy diagram they have. You can see here, they have this sliding window. So these are queries, these are keys, these are K primes. So normally you would just have this here, but you have a third axis that you add, and you would usually just, so your windows are defined as W1 and W2. So you can see here, this is your window shape, and it grows starting with a window size of 1 because of causal masking, and it grows as you increase the sequence length until it reaches full window size. This is just normal sliding window attention. It's just, it has a third axis for your window size. I would imagine you would want to change the window size depending on what modalities you're using. For example, with audio, you may want a larger window size than with images, depending on how you compress your data. So the choice of window size here just seems arbitrary for the sake of making the computation very similar to that of normal quadratic attention. But yeah, I don't want to, it's just, if you know flash attention, it's just adding a third axis. I don't want to, there's not really much to really go over. It's just if you know flash attention and you've looked at the code before, I would take a look at the end, take a look at the appendix. I can show real quick. They basically just add, they have two loops here. So you have your main loop here, which is what you normally have, going over your row. So just accumulating over your row into your, and you compute your accumulation here along with your maxes, like your maxes and your L values here, so that you can do the online softmax. But you have a second loop, which is right here, which is for your third axis that you're adding. And you do this trick right here, where you can just do this Hadamard product, or not, where you just do this scalar-wise product on Q and K, and then you do the dot product whenever you see K prime in the inner loop here, right here. So that's all I really want to mention about that. They have an efficient way to make it computationally similar to normal attention. And since this is sliding window attention, it increases, well, linearly, because it's O of n by W1, W2. So these are constant. This increases with the sequence length. So you can see here, that's what happens to simplical attention, increases like that. While Fav3ms, which is dot product attention, quadratic attention, increases quadratically. So I mean, that's what you would expect. They show that there exists a sequence length such that theirs is better. So that's, yeah, it's computationally fine. They also derive all the gradients if you want to look at those. There's nothing really to say about those, except they derive them, and that's cool, so that you can actually go and code this thing. So now the results. So they've made this thing efficient by defining sliding window attention, and they made a kernel for that. So how does this do? So they basically use a Mo model. So they define a Mo model. They trained models from 1 billion parameters to 57 billion, or active parameters, and they have 3.5 billion. Wait. All right, they train various models. And basically the thing I want to mention is for the simplicial attention mechanism, for the simplicial attention transformers they use, they're not actually all simplicial attention. So they say here, we use inner leaf sliding window to simplicial attention, where every fourth layer is to simplicial attention layer. So every fourth layer is a to simplicial attention layer. They don't say what the other layers are, but I'm guessing those are quadratic attention. So that means that the transformers they're using are not pure simplicial attention. And we'll see that given just adding some layers that are simplicial attention, the model does seem to do better on the, like at a larger scale. So like for the small scale, it seems to do worse over the benchmarks they choose, but for the larger models, it seems to do better than the normal transformer. So that's interesting. Just adding some simplicial attention layers seems to do better. Maybe this is because they can do these triplet interactions as opposed to just pairwise interactions. But it does seem to do better if you scale your models to be large. They also mention that, so normally if you change your model architecture, they mention that so you have your scaling laws, your scaling law here, which basically says this is your loss, and your loss it can be modeled by your model, and your model is defined by kind of two parameters. You have the number of parameters and the number of tokens, or the data you have. And basically they say the loss is defined as like the scaling law loss is you have your entropy from your text, so you can't do anything about that. This is just a constant term, and the minimum value you could possibly get is this right here, just loss is equal to that value. So you can't get any lower than that value because you're not modeling anything at that point. This right here is basically your model being bad. So how much worse is it than the entropy of the text? And this right here says there is error because your model is small. So the bigger your model is, the more parameters your model has, the lower this will be. And that's controlled by n, and alpha basically is the exponent on that. And this right here is the same, but for data. As you increase your data, this value will decrease. So d right here is your data. And as these go to infinity, this will go away. So as you increase these, those will go away, and you will basically get the minimum loss you could get. They say here that it doesn't matter, like they want to look at this, and they don't care about this term here, because the data they use is constant, so they could just ignore that. And they basically fit this, they basically fit the equation, find the alpha values and the beta values, which they define beta right here. It's not as important as the alpha values, because the alpha value basically says as you increase your model size, how much lower is your loss going to get. So as you increase, here they show that alpha is larger, which means as you increase your model size, the loss will go down faster. Or at least the scaling is better. So, I mean, that's what it means. It means the scaling is better for 2 simplicial attention. They say here, we see that 2 simplicial attention has a steeper slope, alpha, i.e. a higher exponent in its scaling law compared to dot product attention transformer. So basically, 2 simplicial attention scales better with respect to the number of parameters because of this higher alpha value, at least for the few things they have tried out. For the few, they basically fit this to their 3 models up here. So, and they show here that it's highly confident, they're fit, but still. They basically say that normal models kind of just shift this value around and they kind of leave alpha the same. So normal changes in your architecture don't really change alpha, but they show here that theoretically changing and or theoretically and empirically, or rather just empirically, not theoretically, they don't theoretically show anything for alpha. They show empirically that if you add this third axis and you use their 2 simplicial attention mechanism, the scaling laws for the number of parameters you got change. So that's an interesting sign. Something you don't get with normal architectures. Now, I'm curious if this actually holds, or maybe not. I don't know. We'll see if this is used in the future. But yeah, basically that's 2 simplicial attention, which is not really using simplices, but I do think it's a cool idea. In the end, I think this will be more useful for, maybe not for self-attention. I don't know how much, like if this is worth using for self-attention. We'll see as more people experiment with it. But it definitely is useful for 3-dimensional modalities. For example, if I want to do two conditions on one modality, so I could do 2 cross attention layers, or I could do 2 simplex attention layer. While the 2 simplex attention layer should be a lot better. Like it should be a lot better because you're doing all triplet interactions, while 2 cross attention layers isn't. So yeah, I do think it's a really interesting architecture, and I'm curious to see, does this work as well as they say it does? Because they are doing signing window attention. Like you can't do this full triplet attention because that's computationally infeasible. So does it work as well as they say it does? I guess we'll see as more experiments come out.